again? If two angles of one triangle are congruent to two angles of another triangle, then those two triangles are similar. Make sure you fix that in your notes. It's just supposed to be the squiggle. Alright, questions over that one.
Also, congruent, just put
Another theorem that we can use to show that triangles are similar. Remember last unit we talked about how triangles are congruent, meaning they're the same. This unit we're going to be talking about how they're similar. So side, 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 similarity. Meaning if the measures of the corresponding sides of two triangles are proportional, then the triangles are similar. Okay? So if we take this side, PQ, over this side, TS, that ratio will equal the same ratio as QR over SU, and the same ratio as PR over TU. Those ratios will all be the same. If that happens, then we know that these two triangles are similar. Not congruent, make sure you fix it. Similar. Questions over that? So if the ratio, so if all the sides are the same, then the triangles are similar. And then side angle side similarity means that the measures of two sides of a triangle are proportional to the measures of two corresponding sides of another triangle, and the included angle are congruent, then the sides are similar. Meaning, if two sides are proportional, meaning the ratios are the same. So if PQ over TS is the same as QR over SU, the ratios are the same, and that angle in between those sides, so angle Q and angle S, if those angles are the same, then we know those triangles are similar.
Because side angles are.
Yep, similarity. Similarity. Okay. Questions over that? Similarity of triangles is reflexive, symmetric, and transitive. Meaning, if triangle ABC similar to triangle DEF, we're allowed to flip that using the symmetric property. So triangle DEF is similar to triangle ABC. Those properties apply to similar triangles. Questions?
Let's try some out. See if we can recognize it. I feel like some of these are a little easier. There's only 3 choices to choose from right now. Let's go through here. So are these triangles similar? If so, state what theorem you use. Well, the reason I say it's easy is because all the pieces are really marked for the most part. So I ask myself right now, what pieces do I have? Do I have any sides that are indicated that there's measurements for any side? Is there any side marked on this picture? Sides. Any sides? Nope. So guess what? Can't be side, side, side. Can't be side, angle, side. That's out. The only choice I have is angle, angle. But angle, angle, remember, tells you need to have 2 angles that are congruent. As if I look right now, do I have 2 angles that are congruent in each of the triangles? No. I've got one. I've got this box in each one, but I don't have that. So off the bat, as it sits right now, I'd have to say no. But here's the problem with this. I have 2 angles in a triangle. Is there a way to figure out that third angle? Just to check it, see what it is? How do I figure out a third angle in a triangle? What do I need to do? Well, add them up, set of 180. Very good. Let's basically subtract it. So I'm going to do 180 minus 39 minus what else? Not 51, same one triangle. 90 is the other one. And that will tell me what that missing angle is. So what is 180 minus 39 minus 90 or 129? Alex, pretty good. 50 what?
No.
You sure? Try it here. 50, I like the 50. 51 degrees. Now, what do you notice about these two? It's a 39 and a 90. It's 129. Do I have 2 angles that are same now? Yeah, I do. So since I have 2 angles that are same, I can now say these triangles are similar. What reason? Well, we have angle, angle, similarity. Someone's going to ask me here, someone's going to try to do it. Do I need that similarity symbol on the end? Yes, you do. I know there's not one for angle-angle symbol or angle-angle congruence when we did the congruent triangles, but we did have this. I did have side, side, side. If I don't put that squiggly there, you'll see an example later today. If I don't put that squiggly there, that's saying that the triangles are congruent. The squiggly, the similarity sign, says they're similar. So the ratios are the same. So we're going to look at that. We'll do an example later about that. All right. So look at this one right here, number 2. Ask yourself what. Yes.
So can you add all the angles together and say equal 180? Doesn't equal 180, and then assume that's not.
That's not. Well, we know it's going to be a triangle, so we know we're assuming it's going to be 180. That's not a bad way of doing it. If I had a number here, that would be proving it's not a triangle. We're telling you it's a triangle, so you don't have to do that. So we're telling you it's going to add up to 180. He's got to figure out the missing piece and see 2 angles the same. If let's say I did this one. Let's say I did this one over here and it was a different angle. They weren't the same. Then they won't be similar. So if I had 2 blanks here for some reason, I knew that was congruent to that. They would not be the congruent triangles because the 2 angles would not be the same. So you would see that within that triangle. Good question. This one right here, I like to ask myself, what pieces do I have? Well, am I given 3 sides marked on here, or 3 sides marked anywhere on there? Only 2 sides, right? So guess what? Can't be side, 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 right? So it's either going to be angle, angle, or side, angle, side. Those are the 3 choices we have. Well, that's a problem because I need to have that angle included. It's got to be in between there. It's in over here in between there, but I don't know what that angle is yet, so I can't say it. I've got 2 sides that look like they'll be proportional, but I got to figure out that angle in the middle. Is there a way to figure out this angle in the middle? Well, I'm sure there is, because how I'm asking you. But what kind of triangle are these triangles? Gary, what are they? Very good. You remember how he's right. Second, these 2 sides are equal. Isosceles. That's exactly right, Gary. If I know the 2 sides are congruent, and these are isosceles triangles, that they're base angles. That's the important thing right there. Their base angles are also congruent. Now that I have that, can I figure out what that vertex angle is?
Yeah.
Yep, and it's just like I did a second ago. I'm going to do 180 minus 68 minus 68, or you can combine it, I don't care how it works. And that will tell me what that angle is, that included angle, that vertex angle. So what is 180 minus 68 minus 68? Alex? 44 is correct. So this is 44 degrees. So now let's analyze this. We said 2 sides are proportional. Yes, the larger one on the left, smaller one on the right. But are those included angles exactly the same? Is the included angle exactly the same in between the 2 sides? No. So are these triangles similar? No. So what I'd say is not similar. Not similar. And there's my work. I labeled my picture. Said not similar because these angles are not identical. If they were, then yes. But they're not, so no. Let's look at the last one. Again, I like to stop and think about what pieces I'm given. Do I have any sides indicated here? Any sides marked? No sides. So it's not going to be side, side, side. It's not going to be side, angle, side. So my only option is angle, angle. But how many angles do I have within each triangle? Just 1, right? 1 that's marked. So this has got to be a no, right? This has to be a not similar. Not similar, right? Good? I only have 1 angle. I only have 45. Trick question. Give you a clue. It is similar. But why is it similar?
Because the vertex angles are the same.
The vertical angles are in there. So now I have those 2 angles that I have. So I have 1 there, 45, 1 arc. I don't know the measure, but I know they're the same. Blue arc and 45. So what pieces do I have now? 2, and they are angle, angle, similarity.
So basically they're all angle angles.
No, not all of them. Just happen to be those 2 examples. Middle one here. Okay, let's look at the next side. Now, sometimes they're marked. If you look back here, they're marked. They have the tick marks. What if I have measures? How do I know what side goes with what? especially if they're oriented different directions, facing different directions. How do I know the 45 is here and the 45 is over there? Well, we've got a way to help you out. So when writing ratios of each pair of corresponding side, the short side goes with the short side, middle goes with middle, long goes with long, and that's how we're going to set this up. I like to stay consistent. When I think about organizing this, just like English language, I'm going to go left to right. So I'm going to start with the small one, go to the big one. And I'm just going to set up my ratio so it's consistent throughout. So when I do so, let's match these up and figure out the ratios of each side. I'm going to do the left side over the right side. I'm going to have three ratios I'm going to set up because I have three sides. So I'm starting at the left side. I'm going to look at the smallest one first. So in the left triangle, what is the smallest side? Not your question. Look up here on your paper. What side is the smallest? The triangle on the left, correct. SC, which is what measure? 6. That is the smallest side of that triangle. Now, I was on the left side, now look at the right triangle. What is that smallest side of the right triangle? Oh, no. There's one person going here. Good. All right, hold that thought. Now I'm going to go look at the next one here. The next side. Still going to do left over right. Why am I writing this little legend thing over here, this little key? Because it's going to keep me organized. A lot of students, especially do this, we have other shapes. We go quadrilaterals and other things too, trying to compare those sides. You get mixed up. It's like, well, what do I know? Which way do I go first? Some people go left to right first, and then on the next one they go right to left. It throws off your ratio. You don't want to do that. So, 6 was the smallest side. What's the medium side in that triangle? Justice, what's the medium side? Well, just tell me with the numbers. It's fine. 8. 8 works for me. 8. What's the medium side in the other triangle? 12. Now we'll look at the last one here. Still do left over right. What's the largest side in the little triangle on the left? 10. 10 over 16. Nice. So as I look at it right now, again, what was I given? I was given 3 sides. So most likely I'm going to have side similarity. So I have no angles listed. But look at the sides. Are these sides, do they have the same ratio as they sit right now? Are these all the same numbers? No. But what do you need to do to fractions every single time you have fractions? Simplify them. So what is 6 over 10 or 9 reduced to, excuse me? And again, you need calculators. Can't stress this enough. Because if you try to use our borrowed calculators to do this, depending on how you get it, you're going to get a mixed number. It's not going to give you the decimal. It will be 2/3. Or all you do is think about what number goes into both, the largest number that goes into both 6 and 9. 3 does. Goes in here 2 times, goes in here 3 times. Let's look at the next one. What is 8 over 12 reduced to, if it reduces at all? What is it? 2/3. Some students say, oh, I can stop right there. I don't have to go any further. If that's 2/3, then the other one has to be 2/3. No. There are some scenarios where it will not be the same. Let's double check and see if it is the same here. 10 over 15 reduces to, Megan? 2/3. So, are the ratios the same? Are they all proportional? Do they all have the same number? Yes. So these are similar. And then ask yourself, what pieces was I given? What pieces? There's only 3 choices. Angle, angle, side, 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 or side, angle, side. Side, side, side. Side to side, side, side. What else do I need to include?
The P thing.
No.
Similarity.
The similar symbol. Side, 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 similarity. Or, yeah, side, 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 similarity. They are the same. If I don't include that, there's no arguing. When we have a quiz or something, if you don't include that, if that's gone, that's saying that these triangles are congruent. They're exactly the same. CPCTC. Those are not exactly the same. So you are wrong. You must include a similarity statement. All right, let's look at the next one here. Just doing a pre-read right now, thinking what we're thinking. What property do you think we're going to use to prove if these are similar? And we're using angle, angle, side, 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 angle, side. So side, angle, side might be it, if it is. Well, let's do the thing, compare the sides. I'm going to do the left triangle over the right triangle. On the little side first. What is the smallest side in the left triangle? 2. What's the smallest side in the right triangle? 4. There's one side. We know it might be side to side because we know already off the bat these angles are congruent, those included angles. So the other one's going to, that's not my formula. It's going to be the left over the right. Left side, next side is 3. What's the other side? 6. All right. As it looks right now, those angles are not the same, but I should always reduce my fractions. What's 2 over 4 reduced to? 2 half. 3 over 6 reduced to 1 half. Good. So are those ratios the same? Are they proportional?
Yep.
Do we have that angle that's included in between there? Is that congruent to the other angle?
Yes.
Yes. So now I can say these triangles are congruent, or similar, and what's my reason? Side, angle, side, similarity.
Okay, we're done.
I don't believe so. I think we've got another one over there too. So this is a scenario you see a lot when we have similar triangles. This isn't like a reflexive shared side, but it's something always happens here. So what pieces was, again, do it first, we recognize there's 2 triangles.
Yeah.
We have a little triangle KLP, little guy right there, and we have KMN, the larger one. It's actually sitting on top of it. Now we don't have a shared side going on like we do in the past. We don't have vertical angles. But when you see triangles like this, there is something they always have. Gary, do you know what that something is that they have?
They both have, they both have same size, same angles.
I like your angle. The sides aren't the same, because I know this one's 8, and this whole thing is whatever that is. This is 12, the whole thing's there. But they do share something. Notice how they're sitting on top of each other. It's kind of pushed in the corner. They're actually sharing this angle right here.
Oh, wow.
So that angle is shared. It's almost like a shared angle situation going on. So thinking about what pieces I have, I'll just leave a little triangle. I have a side, angle, side. The larger one, I have a side, angle, side. So now we're going to have to match up these ratios. I'll do left to right again. Look at the little triangle first. What's the smallest side in the little triangle? 8. In the big triangle, what is the smallest side? Be careful here. What is it? 10. Because I know it's 8 here, 2 there, together gives me a 10. Correct, that is 10. So now we do the other side. I'll do left over right. Then left over right, the smaller the big one. The smallest side is 12. What's the larger side? 15. Let's add those 2 together again. As it looks right now, I know I have K is congruent in both those triangles, but I have to reduce my fractions. 8 over 10 reduces to? What number is both 8 and 10, the largest number? 2 does. And what is it? 4/5. What's 12 over 15 reduced to? 4/5. Are those sides proportional? Are the ratios the same? Yes. So now I can say these triangles are similar by what reasoning? What pieces do I have? Side, angle, side. Similarity. Questions on those? Again, when in doubt, just set up ratios and help you reduce. Well, those are congruent triangles. We're no longer doing congruence. Again, there's tricks with these as well. All right, let's move on to the next phase of this. Skip that one right here. Move on to this one. Because that was just proving it. We don't need to prove it. You know what it is. Well, we still have proofs. But we're just not going to show it. We're proving why that reason works. We don't have to. So now we're going to talk about this concept of indirect measurement. Let's skip that for right now. We're doing indirect measurement. What the point of indirect measurement is, I'll tell you why. So we can find the measurements using the fact that polygons are similar. This is called indirect measurement because we are not measuring the figure, but using other information that we know. I will use this example for you because, again, I like doing examples, tell you what it is. Has anyone ever been out to California? People have been out to California. What's something California and Seattle's famous for? Do you guys know? Something really tall out there. Wait, well, the bridge. Grand Canyon's not there. Okay, that's out more than but more so, the trees. They have the giant redwood trees. The trees are well over 200 feet tall. They are the largest organism on Earth. You guys know this. It's the largest living thing on Earth. Now, how do you measure? Yes, it's a tree. How does measure? Do you think someone climbs up there with a measuring tape, dragging them behind them, trying to measure how tall it is? No, they don't. They use math because it's a lot easier to use math to figure it out versus climbing up there. It was not as fun, but that's how he could use it. Again, this tree out here, Carl. You guys ever met Carl out here? This big tree, nice, lovely tree. How do you measure how tall a Carl is? You gonna go up there and measure it? No. I don't know, but how do you get up there? If you're cutting a tree down, you know why you measure cutting a tree down? Because it's not long enough. If your tree's too long, you cut it down, it might hit your house and destroy your house. So you gotta make sure if I cut it, it's not gonna hit it. So how do I figure out how tall something is without actually measuring it? Because some things are too tall. Well, you're on the right track. We will do some trick down the road, but there's another way we do it, using indirect measurement. And I'll show you here. So we're all going to go pretend we're out in France checking out the Eiffel Tower. Because I know a lot of you guys are wondering, how tall is the Eiffel Tower? Well, you're going to find out today. 500-something feet? Nope, we'll find out though. So Nina was curious about the height of the Eiffel Tower, like most of you guys are. She used a 1.2 meter model of the tower and measured its shadow at 2 p.m. The length of the shadow is 0.9 meters. Then she measures the Eiffel Tower shadow, and it was 240 meters at the same time. How tall is the Eiffel Tower? Again, you're not going to climb up there and measure it, figure it out. So here's what we're going to do. I recommend drawing a little picture. So you guys get to be your best little artist selves and draw a picture here to help you understand what's going on here. So I'm going to go ahead. I'm going to draw the little model tower first. So here's my baby Eiffel Tower. Baby Eiffel Tower. There's some X's in there. All right. There's my little model Eiffel Tower. And I'm also going to draw the real thing. The thing that people see in France all the time. There it is. There's some cross stitching right there. And then it gets really small and narrow. There we go. There is the large Eiffel Tower. Let's go through some label information we know. How tall is that little model? Yes. One. Okay. Impressive. We'll see if you're right. So it's 1.2 meters tall. All right. It's weird math because this is in meters, not feet. Maybe Google helps out. But we'll find out. So now, how tall is the real one? Do we know? No, we don't. So we call that X. Now he told me in feet, didn't tell you in meters. So there is that. We also have a shadow. Well, here's something else you need to draw. You need to have a sun in this picture. So you guys are going to draw a little sun over here. Because every time a sun is drawn, it casts a shadow. Okay? Have a little red in there. Make it nice and toasty. And we all know have sunglasses.
And a smile.
Well, of course they have smiles. So there's that. They have sunglasses. He's really happy. Sunglasses, sunglasses. All right. Well, suns, they're going to cast a shadow. So their rays are coming down. It's going to be hard to see, but here come the rays. Bring it down. There's a ray coming down there. And we always know that when they have shadows, they make blue shadows. Everyone knows that. Everyone knows that suns make blue shadows. Well, look what I really just made. What sort of shape did I just make based on these Eiffel Towers? A triangle. All right? And that's really what we're doing here. We're making triangles. Now, on the little triangle, when we measure that shadow, how long is that shadow on the little model one? Nope. 0.9. Yep. What is the shadow on the large Eiffel Tower? 240. Awesome. Well, I just made two similar triangles, because then we know they're going to be proportional. Well, now how do I go about solving this? Well, I'm going to do just like we did before. When in doubt, proportion out. I'm creating a proportion here. You have to see how that rhymes? What? This is 0.9. You want to put a 0 there to help you out? 0.9. That's just how long the shadow was on that guy. So I'm going to do my triangle like I did before. I'm going to do the left triangle over the right triangle. Well, let's pick the smallest side. What is the smallest side in that little triangle? The 0.9, right? The 0.9. Over. What is the smallest side in the right one? Be careful here. Look how it's oriented. A lot of people say X. But if I use 0.9 as the smallest side over here, what's going to be the smallest side of the other one? 240. That will be equal to something over here. Now we go to the next side. If I use 1.9, or 0.9, what's the other one I got to use? 1.2 over what? What side matches up with it? X. Well, look what I just did. I created a proportion. How do I solve proportions? I.e., what was number 2 question on your little skill check?
Cross multiply.
That is correct. Going to cross multiply. And you're going to set up an equation with this. When I do so, I'll help you out with the math. I will do the first one for you. It's going to be 0.9 times x is 0.9x is equal to, what's going to be the right side? What is 240 times 1.2? Again, you should be trying this out of your desk, trying this out. It is, I heard something, what do you say? 288. 288. What last step? Last step here. Divide by 0.9. Those go away. This side's going to be 0.9. So how tall is this in meters? So 320 meters. That's how tall the Eiffel Tower is. Without physically climbing up there and getting it. And if you Google it, you check it out on Google, you got to look at what it is in meters, Gary.
Okay.
And it would be
I'm on
324 meters. They did not account for the antenna on
See
top of
the
it.
shadow, the 0.9 was probably around it.
Mhm.
So we had the exact long decimal.
Yeah, it would make sense. That's how tall. That's really how tall the Eiffel Tower is.
Google it.
Pretty cool. Yeah. I got pretend there's an antenna we didn't count for. All right. Plus all those are just making triangles. Like I said, because we rounded this, it's not exact. Pretty dark close though.
Okay, let's start fast.